Hello everyone, my name is Engin Ermis. I'm a fourth year computer science student at Bilkent University. Today I will explain you my Physics 102 final project. The physical background of my experiment is the theory of parallel plate capacitors. Like in an ideal capacitor, as you can see by this formula, if you increase your plate areas in capacitor, you should see a linear increase in capacitance. And similarly, when you increase the distance between your plates, you should see a linear decrease in capacitance. And in my experiments, I tested whether the theoretical formula holds for real-world environments as well. And if we have errors, which we have, what are the sources of those errors? And which variable, whether the plate area or the separation distance, have more significant effects on the capacitance value in real world. Okay, so now I will explain you my experimental setup. My experiment consists of two parts. In the first part, as you can see, I use this circular plate capacitor available in our physics laboratory. In this part, I kept the plate area constant. This circular plate has a diameter 17.5 centimeters and changed only the distance between the plates. Then I measured the capacitance for different separation distances between these plates. And in the second part, I prepared square plates by covering cardboards with aluminum foil. In this part, I kept the distance between the plates fixed at 1 centimeter and changed the plate area by using different plate sizes. Then I measured the capacitance for each plate size and compared the results with the theoretical values. Okay, now I will share you my results. So this is for the first part of my experiment, where I changed the distance between the plates. The first thing that you can notice is when we increase the distance between plates, as the formula suggests, we see a decrease in capacitance. But also there's an increase in error, and this is the plot for capacitance versus inverse distance. I use inverse distance to see a linear relation. So although errors may seem high initially, when you get the slope and extract the permittivity constant of the slope, there's only 1.1% difference between the theoretical value. And the main reason of errors in real world, the electrical field lines are not perfectly uniform between the plates. And that's why there's an increase in error when you increase the distance between plates, because there's more deviation. And this is the result for the second part of the experiment. And this is the plot for capacitance versus plate area. So for this part, again, our findings are parallel to the formula. And again, using the slope, when you extract permittivity constant, there is a higher deviation than the ideal one, which is around 10%. In prior experiment, there it was only 1.1%. And one of the main reasons is the plates are handmade, right? Like in this part, the prior experiment used a real capacitor in laboratory, but since they are handmade, the geometry is imperfect and rough, which definitely affected the uniformity of the electrical field lines. Okay, so in conclusion, our findings are very parallel to the theoretical formula, especially for the first part. Like in the second part, there is slightly more deviation, which is something normal because the plates were handmade. Aluminum foil wrapped cardboards, they were handmade, so the electrical field lines between plates were not perfectly uniform. And although initially the error values may seem high, it is mostly due to the sensitivity of this experiment, because even 1 picofarad change can result in 10% error. But as you can see, when you calculate the slope, the overall resemblance are very high. So we can conclude that the theoretical formula holds for real-world environments as well, with small deviations.